Today we continue our exploration of alternating current. We're going to review our phasors. We're going to do a quick review of transformers, and then we're going to talk about resistance of wire. And it turns out all three of these are related. We started this class with direct current. So these were our DC rules. We had Ohm's law, we had KVL and KCL, voltage dividers, current dividers, and the concept of power. All of these have transitioned into phasor form, where we picked up inductors and capacitors. Transformers were briefly introduced. Today we'll talk about wire size, and in future topics we're going to talk about generators and motors. All of these ideas will loosely tie together into something we'll simply call AC power. In industry, we'll typically encounter a three-phase system. We'll assume this is a 480 volt AC system, which means that each generator or each phase would have 277 volts relative to neutral. We'll let this be phase A. We'll let this be neutral. So phase B, 277 volts at a phase angle of negative 120. And C would be 277 volts at a phase angle of 120 degrees. I don't want to get into all the calculations today. However, we can explore a single phase load connected up to this system. We'll assume some wire resistance, and then we'll let our load be connected here between phase A and neutral. We'll let our load be 1.5 ohms. We'll let this be J 0.87, and we'll let the wire resistance be 0.02. One of the questions you might ask is, what is this voltage out there? We'll look at this calculation two different ways. First, we'll do it the hard way, and then we'll do it the easy way. So the hard way would be to say the total impedance of this system is 0.02 plus 1.5 plus J 0.87, which gives you a total impedance of 1.52 plus J 0.87 ohms. From there, you could calculate the current, which is a voltage, in this case 277, at a phase angle of 0 degrees over that impedance, so 1.52 plus J 0.87. Run that through your calculator. So we'll turn it on. Make sure you're in complex mode and make sure you're in degrees. And then go ahead and enter your number, 277, divided by parenthesis 1.52 plus 0.87J, close the parenthesis. And then shift complex 3. So we want everything in polar mode because that is what our meters will read. And in this case, our meter would read about 160 amps at an angle of approximately negative 30 degrees. Again, we were looking for the voltage as measured at the load, while we have this current here flowing. And we can calculate that as voltage at the load is 160 amps at a phase angle of negative 30 degrees by the impedance of the load. So in this case, that's 1.5 plus J 0.87. So voltage as a phasor on the load is equal to, all right, so our current's already entered, so we'll multiply that by 1.5 plus 0.87J, close paren, equals. Again, we want to put this back into polar mode, so shift complex 3, and this tells us that we're going to have approximately 274 volts at a very small angle. We may as well call that 0. So the voltage on the load can be approximated as 274 volts, which means that this piece right here, we lost a couple of volts across that. So about 3 volts was dropped across that resistor. Again, that resistor represents the wire that's in the circuit. All right, that was the hard way. Let's do the easy way. And I would argue the easy way is with a voltage divider. We would have said the voltage of interest is equal to the impedance of the interest over the total impedance multiplied by the source. In this case, the voltage of interest is the load voltage. Again, it's the voltage right here. And that would be 1.5 plus J 0.87 over 1.52 plus J 0.87 multiplied by the source voltage, which was 277 volts at a phase angle of 0 degrees. Run that through a calculator like this. Remember to use the parentheses. 1.5 plus 0.87J, close paren, divided by 1.52 plus 0.87J, close the paren, equals, multiplied by 277, gives us, in polar form, 274. About 274 at a phase angle of about 0 degrees. Sorry about that. Looks like my pen slipped here. This should also have been 274. Right, 274, 274, and 274. I think you'll agree the voltage divider is a bit easier to use. It's a single step as compared to the two-step process where you had to figure out the current and then figure out the voltage drop using Ohm's law. We should focus in on this wire a little bit more. And the term I'd like to introduce you to is I squared R loss. So power is equal to the current squared by the resistance. And this equation allows us to figure out how much heat is given off in the wire. That may sound like a silly statement, but wires do indeed get hot. In this case, the power is 160 squared by 0.02. So that's 160 times 160 times 0.02, which is about 500 watts. You could look at this with the aid of a power flow diagram. Here we have the power lost to the wire. Again, that's about 500 watts is lost while the wire is delivering about 38 kW. What would happen if this resistance doubled? We'd say power is equal to I squared R. For this example, let's assume that that current stays at 160. So power is equal to 160 squared by 0.04. If you run that through your calculator, I think you'll find that we now have 1 kilowatt of loss in that power line. To put that into perspective, 1 kilowatt is approximately equal to a small space heater that you might purchase, which is also equivalent to the power that a hairdryer or a hot plate might consume while it's operating at full power. We can consider this line loss by looking at how it applies to transformers. To save some time, we'll assume the same conditions as our previous example. where this is 1.5 ohms and this inductor is J0.87. We'll have a voltage of 277 volts, phase angle of 0 degrees, and I believe the current was 160 amps at a phase angle of negative 30 degrees. This is transformer 1, transformer 2. This is a 1, 2, 3 step up transformer. This is a 3, 2, 1 step down transformer. And our line resistance is 2 ohms and 2 ohms. And what we're curious in is what is the power lost in these resistors. And these resistors represent the wire resistance between the two transformers. From your note card, the number of turns on the primary over the number of turns on the secondary is the voltage on the primary over the voltage in the secondary. And current is upside down, with this being the current in the secondary and this being the current in the primary. In this example, the current in the secondary winding of T2 is that 160 amps. So we could say that 3 is to 1 as 160 amps at a phase angle of negative 30 degrees is to the current in the primary of T2. Solving for that current, so current in the primary of T2 is equal to 53 amps at a phase angle of negative 30 degrees. Anywho, now that we have this current, we can now calculate the I squared R loss. So the power lost in the wire is equal to I squared R. So the power lost is now, I believe it was 53 amps. Yep, so just 53 squared by the resistance, which in this case is 4 ohms. So the power lost is 53 times 4, which gives us about 11 kW, which is absolutely atrocious. We'll call this a failed design. We have two options. We could replace the wire. We could purchase new cables that have lower resistance, and that would allow us to get the power loss down to something reasonable. Or, and this is the option we'll take, we're going to replace these transformers. Instead of a 1 to 3, we'll go a 1 to 10, and we'll use this as a step down of 10 to 1, which means our current is no longer 53 amps, our current is now 16 amps. So that is the current in the primary of T2. So now if we go back and do this calculation, our new power loss is not 53 squared, it's 16 squared by 4. 16 times 4, and that is 1,000. So about 1,000 or 1 kW, which is a significant improvement over our original loss of 11 kW. Again, we've kept the same wire resistance in this case, but we've increased the turns ratio on the transformer, which means instead of our original voltage, which would have been 277 times 3, so instead of having 831 volts as measured here, we now have 2,770 volts as measured at the primary of T2. And I'll leave that as an exercise for you to do that calculation using this piece right here. We should put this into words. We would say that higher voltage yields a lower current. And that's assuming we have the same power. Higher voltage also implies a lower cost for the transmission line. Instead of suspending a large wire, we can use a much smaller wire to do the same job, and that generally lowers the cost. You could also argue that a higher voltage improves the efficiency of the system. When we talk about efficiency, we generally show things as that power flow diagram. So, in this case, we could talk about the power in the transformer. That's XFMR1. And there we'd have something called core losses and I squared R losses because of the wire that makes up the winding of the transformer. We could talk about the transmission line itself. Again, we did talk about that. We mentioned it has I squared R losses. Then we arrive at the second transformer. Once again, XFMR number 2. We have core losses and more I squared R losses because of the windings in that transformer. Next, we'll assume we're driving a motor. So we're going to have power lost there. And that's due to something called core losses, which we'll explore in a few more lectures. The windings themselves, then something called windage, and friction. Till we finally get to the part we wanted, which is mechanical power out. Again, efficiency, eta, is our power out over our power in. So this is our power in, this is our power out. And all of these are power that's lost in the system. If you're curious, we can talk about the typical efficiency of our various machines. So a large motor is approximately 95% efficient. A small motor, not so good. The motors you find in your house are typically in the neighborhood of about 80%. A large transformer, an impressive 97%. And if you're curious, something like a diesel generator, when you consider the fuel in to electricity out, you'll be lucky if you get about 40% efficiency. We could chain these together in a hypothetical system. So we'll let this be your diesel engine driving a generator, which feeds a transformer with some wire loss in the transmission line, feeding another transformer to step the voltage back down, and then we'll assume that there's a very large motor here. The diesel has an efficiency of about 0.4. The generator will have about the same efficiency as a large motor, so we'll call that 0.95, our transformer, 0.97. Our wire for our power line we'll assume is 0.90. Then we're at the transformer again, and finally at a motor. That's a lot of numbers, and if you wanted to know the efficiency of the total system, you could simply take and multiply all the numbers together. So the total efficiency is 0.4 times 0.95 by 0.97 by 0.90 by 0.97 by 0.95. Which gives us about 31%. When we consider the fuel we dump into the generator and the power we get out of this hypothetical motor. As a sidebar, we might want to mention something about cost. So this is the cost of the system, and this is the total efficiency. The curve would be something like this. So the more efficient we make the system, the more it will cost us. We should note that there is a limit, and adding more money will not necessarily increase the efficiency. Keep in mind that you want to stay out of this area here because poor efficiency can cost you fuel and actually more money in the long run, right? It doesn't pay to build an inexpensive, inefficient system. Far better to find somewhere in the middle where you've got a decent balance between cost and efficiency. Let's take a look at something a little closer to home. Suppose you had a hot water heater in your basement. The heater would be fed by a 240 AC source. The current would be in the neighborhood of 19 amps, and you have approximately 50 feet of 10 American wire gauge. So it's 50 feet there, and there's about 50 feet return, again, of that 10 AWG wire. If you take a look, this is probably orange Romex. This wire is relatively easy to identify because it is flat. And all of that is enclosed in an orange insulating jacket and then stapled into the wall. If you were to look up 10 gauge wire, you would find it has approximately 1 ohm per 1,000 feet. In this example, you have 50 plus 50 feet, so you have 100 feet of wire. Using dimensional analysis, we can multiply this 100 feet by 1. And since there's 1 ohm per 1,000 feet, we simply put 1,000 here and 1 ohm up there. We cross off a few of these zeros, so you end up with 1/10 of an ohm. Knowing the resistance of the wire and the fact that there's about 19 amps flowing in that circuit, you can calculate the power lost to the wire. And that is I squared R, which is 19 squared by 0.1. So that's about 36 watts lost to the wire, which means that orange wire that's stapled to your wall is giving off 36 watts while that heater is running. The voltage drop in the wire is a current by a voltage, which in this case is 19 by 0.1, which is 1.9 volts. So your water heater doesn't get the full 240 volts. It gets about 238 volts because some of the voltage is dropped across the wire. If we put this into words, we would say the wire's temperature will be greater than the ambient temperature. And this is something you need to watch out for, especially when we start bundling the wires together, because the wire has to get rid of that heat, you see. In our example here, that wire had to get rid of 36 watts. But if you start running cables in bundles and they get closer together, the ability to give off that heat is reduced, which means the cable will actually end up warmer. And if you're not careful, it'll get warm enough to melt the insulation. This is just one of many reasons that we have codes that describe how wires are supposed to be run and terminated. Before we close, let's look a little closer at wire. We would talk about the length of a wire, and we would talk about the area. The formula for wire resistance is K, which is the resistivity, L, which is the length, over the area. and that's an area in circular mills. With the assumption that we are at a specific temperature, which is typically taken at 68 degrees Fahrenheit. Know that each material has a specific resistivity. Copper, for instance, has a K of approximately 10.4. And we talked about circular mills. In our previous example, we talked about 10 AWG wire. That has an area of approximately 10,380 circular mils. Considering our previous example, we would say the resistance is equal to 10.4 by 100 feet. Somewhere back here, we said 100 feet, I believe. Yep, there it is. So we said 50 feet and 50 feet. Together, that's 100 feet. And that's over 10,380, which gives us a resistance of approximately 0.1 when the temperature is 68 degrees Fahrenheit. Well, we already established that as the wire conducts current, the wire will have I squared R losses, which means the wire will not be at 68 degrees Fahrenheit unless your house is really cold. Instead, it'll be at something higher. We could correct for this temperature if we're curious. I'll leave that up to you, but I can tell you that if the temperature increases to 120 degrees Fahrenheit, we can expect that same 100 feet of Romex to have a resistance of about 110 milliohms. Higher resistance, now you have more voltage drop across the wire, and the wire will get hotter, which would tend to increase the temperature more. Which is something to watch out for. Again, that's why we have codes, so we don't make mistakes and burn the house down. I have one final thought regarding these low resistance measurements, and that is the 4-wire resistance measurement. The argument goes like this. We have a wire. We want to measure the resistance of this wire. Now it's a low resistance. And to be sure, you could take your meter and connect the probes across and you would measure some resistance. However, it's not a very accurate measurement. And the reason is your meter in general can't distinguish from the wire that you're measuring and its own test leads. The 4-wire resistance measurement takes the test leads out of the equation. Schematically, it looks like this. We have a current source. We have the test leads. They have some resistance. We really don't care what the resistance is, but we know that they do have resistance. We take those test leads and we connect them up to our device under test. So this is a low value resistance that we're trying to measure. We need 2 more things to complete this process. We need a voltmeter connected as close to the device under test as possible, and we need a known current. Suppose this was 5 amps of current. That means that there'd be 5 amps flowing this way. There would be 5 amps through one test lead. There would be 5 amps through the other test lead, which means there would be 5 amps flowing through our low value resistance. This voltmeter connected up as close as possible to the device under test would show the voltage drop not of the test leads, but only the voltage drop across our device under test. Knowing this current and knowing this voltage, we can calculate the resistance as a voltage over a current, which is nothing more than Ohm's law. As far as the 4-wire measurement is concerned, you could certainly use a bench power supply, such as I've suggested here, where you inject 5 amps into the circuit. Or if you have the funds, you can purchase a fancy meter that would have 4 wires. So a 4-wire resistance actually coming from the meter. You would have 2 test leads connecting to the device. You would then have 2 additional wires that come out and connect as close as possible to the device under test. These extra wires are known as the sense wires. This is no different than the circuit we had before. We would inject a known current, which would eliminate any inaccuracy caused by the test leads or the resistance of the test leads. And then we have the sense wires, which go back into the instrument. They carry no current, but do tell us what the voltage is at the device under test. And with that technique, you can measure things with very low resistances.